If you look at your tutorial question, so you're having something swinging, or not swinging, but there's a delivery from the top, slide down at a certain angle with the R and velocity. Okay, so before you look at the question, you look at the motion of the particles. Basically, this is a curve motion. It's a curve motion. So curve motion gives you tangent and normal direction. All right. So then you look at the question. So you're giving the mass m, travel smooth circular ramp at the angle. Sorry, this one should be theta. So it should be theta. Has a speed of v. Determine the angular momentum about point O here. Where is the angular momentum? Okay, angular momentum you see as a MOM, moment of momentum. So you need to convert this one into momentum. Again, what is momentum? M mass multiplied by V, you get momentum. Momentum multiplied by the R, you get the MOM. You get the angular momentum. Rate, increase speed, and so on. You need to find the acceleration. Acceleration at the tangent direction. This is curvilinear motion, tangent direction, normal direction. So you start looking, drawing free body diagram. So you draw the box. You draw the box, and then you draw the axis as you analyze the curvilinear motion. A and T. This one you should be very good already. T and N. Put in the angle. All right, put in the angle. O, R, okay. O, R, and then the angle. Okay, this angle is the same as here. I just draw another triangular over here. Right, it's a same triangular. Okay, theta is from here to here. And then once you complete all the parameter, the first force you put inside the free body diagram always your weight or acceleration effect, the weight W. And then for this module, especially when there's a contact between the object and the surface, they always have a normal force. Take note on that. For this module, every time you see in the diagram, if the object touching the surface, there's a normal component there. So I just give some convenient. So this axis here, or distance from O to here, is R sine theta. Why I need this one? Why I need this distance? Because I'm referring to O. You learned about moment before, right? What is moment? Moment is the force. The force multiplied by the 90-degree distance. This is 90-degree distance and the force. F times D. Okay, F multiplied by the distance. You get moment because of the weight here, referring to O. F multiplied by D, like what you learned in your physics, moment. That's why I need to find what is this one. Okay, so V, the velocity is along the tangent. Okay, since the velocity is along the tangent axis direction, we can use the scalar. Again, scalar tell you about what? Scalar only tell you magnitude of your angular momentum. Yeah? Angular momentum, HO bracket Z. You know that the angular momentum is in Z direction. You take D multiplied by momentum. d multiplied by momentum. Substitute the value inside there. Where is the direction of v? V is in t. T r, okay, T r. So where is the motion? Velocity is along t. T and r, it gives you clockwise direction. So when you use right hand rules, where is the z? Right. So if in my case, I'm looking at the monitor, the z, my thumb is pointing into the screen. Okay. If I use right hand rules, t, why I use t? Because my velocity, my v, is along my tangent direction. So my v is here. So v, I tie a string at the end of my velocity. When I swing this object, I get clockwise direction. I use right hand rules. Clockwise will give me thumb pointing into the monitor. So back to our angular momentum here, angular momentum. So that's why the positive direction here is clockwise. Okay, the direction is clockwise because V and R give you clockwise direction. Your Z is going into the screen. What is your D? D is your R. Because your R and T is 90 degree. Your R and T is 90 degree. R is parallel to your normal axis. That's why you can straight away use the T, right? R multiplied by momentum, mv. You have your, in this case, you don't have the numbers, but in this case, it's just a derivation of equation. Of course, this one can extend into a real question where I give you the R value, velocity value. You just substitute there, okay? What is the rate? Rate of increase of your speed is actually you take the V, differentiate with T. You have V, right? You take this equation, this whole equation differentiate by T, means divided by T, divided by T, divided by T. This whole thing divided by T, you can find the increase of its speed. All right, so if you differentiate this whole equation with the T, you get H dot, right? H dot is also equal to momentum. Oh, sorry, equal to moment. How to find moment on the left? Moment, all the moment will equal to the rate of change of your angular momentum. So left hand side is moment, right hand side is your angular momentum. Okay, there are two different things. Left hand side is moment, right hand side is angular momentum. Before the break, we already derived this equation. And we proved that this one equal to this one. So that's why we can use this equation. Right? Important for your test 2. So how to find moment on this object based on O? You will focus on W. How to find moment of your W? There's only one force, right? On this object, on this object, they have two forces. One is the normal force, one is the weight. Normal force pointing along the normal axis here, which is R. And if you learn moment, when the moment is along the axis, you don't have moment. Correct? Okay. This is force. This is distance. So if your force is parallel to your distance, there is no moment created. Same case as your N. That's why the moment here you don't see normal force, but you see weight component. This weight, how this weight create moment? From the O, you take W multiply by 90-degree distance, which is R sine theta, multiply by the force, you get moment, which is W multiplied by the D, F D, mg multiplied by the 90-degree distance, you get moment, equal to the time differential of your R and V. Simplify this equation. R constant, you can move them along. Okay, you can move them along. Move your M constant, move outside, R constant, move outside. So you have dV dt, you get this one. Again, why we can move M and R? Because M, mass constant, R constant, these two constant, you move outside. If you don't move outside, you differentiate with time, you get 0. Right? So same with here. After you move outside, cancel M, cancel R. The answer is rate of increase in the speed dv dt equal to g sine theta. This is the answer for example number 9. Any question? Clear? Everyone clear?
Yeah, so far clear, sir.
Right. Let's move to another one. Okay, you can prove this equation. You can prove these two equations by using equation of motion that you learned in chapter 2 and chapter 3 in the tangential equation, where you can prove this equation by using what you learned in your tension and normal chapter, right? Collinear motion. You still get the same, F equal to ma, direction going down, right? The direction means this direction, okay. So F equal to ma. So what are the total force inside this free body diagram? So all the force in t direction, this one don't have. This one is in n direction. So you split your W in t direction, you get W sine theta equal to ma, a equal to dv dt, cancel m, you get the same answer. Let's look at principle of angular impulse. Just now we look at angular momentum. So now we look at one new concept for today, another after the break. Now we combine what you learn, angular momentum and angular impulse together. Okay, so this is what we learned before this. All the moment on the left equal to angular rate of change of your angular momentum on the right hand side. So you can rewrite this one as this one. Right, with the dot, we just change the dot into dt. Then you move the dt to the left hand side at this form. Okay, you move your dt to the left hand side, you get this form. And since you have dt, you know what you need to do, integration. Right? So when you see dt, the equation is not balanced or not stable. You need to stabilize the equation. You use integration. So integrate, this is a time, integrate time 1 to 2 equal to the change of your angular momentum. Okay, and you move into the form that we're familiar with. You move your angular momentum before or 1 to the left hand side. You get h1 plus the change of momentum, the moment equal to angular momentum after. Do you see the same form that we learned before this? But this one is in the form of momentum and impulse. Previously, I think the first session, we looked at linear impulse and momentum. But this one, we have H here. This one, we call it principle of angular impulse and momentum. Yeah? So we have a few principles in this module. You have learned principle of linear impulse and momentum, right? Before this, you have principle of linear impulse and momentum. Here in these slides, you are seeing principle of angular impulse. Angular impulse, H. And this one is M. A bit different from the one that you learned before this. This is angular impulse, not linear impulse. So look carefully when it comes to final exam. The question might ask you to calculate using a certain principle. Look carefully. So just explaining what is angular impulse here. All right. So you can write in the vector form. Again, when do we use vector form? When the particle move in the three-dimensional axis. You will need to use this one when you study about FEA, finite element analysis, and even high-level simulation, right? So high-level computation. For example, if you learn about robotics, this one also very famous in robotics, where there's a vector movement. So when you write the angular impulse component in the vector form, you can write m equal to r cross f. Again, r cross f is a sequence. You cannot flip. Once you flip, it's different meaning already. R cross f means from point A to point B is a different from f cross r. If you write f cross r, means you're looking from B to A already. So it's a different concept. So we write this one in the vector form or cross product of your r and force, position and force. Moment is F times D, but in this case, because when you use cross product, you are looking at the particles moving in the three-dimensional axis. That's why we have a cross product, and in the vector form. Right. Yeah, this is just a further explanation of what you learned just now. The principle of angular impulse and momentum. What you need, what is the difference between this one and this one? It's just that you add the sum of angular momentum to the before and after. When you have a group of particles, you just add the sum symbol there. All right. I will move very fast. So you have, I just put side by side what you have, what is the differences between vector formula and scalar formula. So on the right hand side here, so on the right hand side here, you have vector, means inside here, you are using I, J, and K inside there, right? Vector form. Scalar formula means you can express them in the X, Y, Z component, yeah? Just for your info. What is the difference between vector and scalar? Vector, you are seeing I, J, K, three-dimensional description. However, in scalar, you can write in X, Y, Z that you're familiar with. Same with this one. So there are two formula. This one This one is a principle of linear impulse and momentum. I think I missed out this one. I think I have a mistake here. This should be M, not F. Okay, so when you talk about conservation of angular momentum, you don't have angular impulse there. You don't have angular impulse when you have when you apply the conservation of angular momentum. So h1 will equal to h2. This formula is conservation of angular momentum. We see this how we apply this one. Okay. And every time you see a sum symbol, it means you look at the system of particles. Look at example, more interesting compared to the theory part. Okay, so what you have here is example number 10. You're having a car move with the force at the shape that you're familiar with. This is a curve shape. So when you move in curve shape, expect in the free body diagram later, you need to draw the normal and tangent direction. Yeah? Every time you look at the question, if the question gives you a round path, the next steps in your free body diagram, remember to put in the tangent and normal axis. Yeah? You're given the radius of 100 meter, and remember when you have a collinear motion, if the radius is not given, there is a formula to calculate the radius. There's a formula to calculate the radius if the radius is not given. Just recall collinear motion. Yeah? So what you have here, 1.5 megagram, again megagram. When you calculate, you need to change the unit SI into kilogram. Circular road, if the traction force equal to F equal to 150 T square Newton, T second, determine the speed of the car when after time equal to 5 seconds. The car initially travel with a speed of 5 meters per second. Ignore the size of the car. We need to use this information. You have velocity before is 5 meters per second. You have the force acting on the car given in a formula. In this one is quadratic equation, 150 T square Newton, and it asks you to find the scenario at T equal to 5. Before you solve, draw a free body diagram of the car. Look at this one. So you have X, Y, Z, right? So you have a car, you have a Z direction, you have a pathway, circular pathway, and you have a weight pointing down, W pointing down. You have, again, every time your object have contact with the surface, there's a normal component there. There's a force pushing from behind. There's a R direction. There's a R direction, or you can see this one as your normal direction. This is your T direction, right? So this force you can see as a tangent direction. This one as your normal direction, but just to fit the question, I use F sub R to represent radial direction. Now we use the principle of angular impulse and momentum in this scenario. Okay. And since we are using the angular impulse and momentum, what is contributing to our equation is the weight, normal force, radial friction force. Okay. they will be eliminated because they act parallel to the axis or pass through it. FR and this one, yeah. So we use the principle of impulse and momentum, angular impulse, principle of angular, not linear, angular of angular. So when you use angular, it should be M and H. So H1 plus sum of momentum T plus your angular momentum. This is angular impulse. Okay. So I modify a little bit to Z direction. HZ1, MZ, and HZ. Okay. I modified the original angular impulse and momentum into the scenario here. I focus on Z axis. Then I start calculating how to find the angular momentum. Again, what is the definition of angular momentum? R momentum, MOM, moment of momentum. What is momentum? MV. What is moment? Times the distance. MV times the distance. Okay. So R MV plus the angular impulse. What is the moment? R times F. R times the F. This is the R. R multiplied by F, you get moment. Okay, you get a moment along the z-axis. MF. Okay. F multiplied by the D, you get moment. That's why here you see RF here equal to your MOM after R multiplied by momentum RMB. C just represent the center of my object. You calculate lah. So R is 100, M is 1,500 kilogram. Although the question give you mega, you need to change into kilogram. 1.5 megagram equal to 1,500 kilogram. Velocity 5 before it start. Before it start, given 5 meter per second. Then this one, your angular impulse. R is given 100. Force is given by an equation, 150t square. Integration with time. This one is your integration chapter in your mathematics. I assume you already mastered, so I will not go deep into how to do integration. All right, it's an integration over t. Then same with this one. RMV2. R still the same, 100. M still the same. V2 we don't know. After 15 seconds, we don't know. And it asks us to find. Determine the speed of the car after 5 seconds. So you put this one in, put this one in here, put this one in here, after you do calculation. So after you integrate this one, and time from 0 to 5 seconds, put in time 0 to 5 seconds, question asks you for 5 seconds. So 0, 5, you do integration, rearrange the equation, the answer is 9.1 0.17 meter per second. Okay. Right. So earlier we explained why the gravity, why the W, N, and Fr is not calculated in here. Because Fr going there, going inside the radius doesn't contribute anything. These two balance each other. So it will cancel out. You only left out the F and R component. That's why inside here, you only see F and R and the momentum, the angular momentum. Okay. Another example, example 11, we look at a scenario. So a 2 kilogram disc at here, start from rest. So your V1 already know, V1 is 0. From a smooth horizontal surface means no friction. Is attached to an elastic cord. You have an elastic cord. This one, you are given the stiffness matrix, stiffness constant. You learned about spring before. So there's a spring force here. Okay, you have a spring force and initially unstretched. So this question combined with the concept of spring and apply with the principle of angular impulse and momentum. If this is given a velocity 1.5 before it start, meaning here before start 0, but is given a velocity d1 1.5 perpendicular to the chord. Yeah. So we have v, we have a distance 1.5, and you learn about the conservation of angular impulse and momentum. So you can change this one into momentum. Momentum multiplied by the distance, you get MOM, you get the angular momentum, right? Determine the rate at which the chord is being stretched and the speed of the disc at the instant of chord stretch 2 meter. You want to find the speed when the length of this rubber here stretch up to 2 cm. Oh, sorry, 20 cm or 0.2 meter. Okay, need to find that one. So basically this question asks you to apply the principle of angular impulse and momentum and some spring concept. Draw free body diagram, 3-dimensional, Z, Y, and X. So before start, you have an object 5 meter, 0.5 meter, right? So you imagine if you kick this object with 1.5 meter with the stretch, with this stretching object, is still going to move in a curve motion, but the curve is not a normal curve, but is moving in a curve motion, right? You can imagine, right? This is elastic. You kick this plate or this disc with a speed of 1.5. No matter how it goes, it still move in a curvilinear motion. And given VD1 1.5, and you want to find the speed here, not speed, the rate of the chord being scratched, this one, at this here, and also the speed during the chord was stretched, 0.2 meter. Meaning, what is the final length that you want to find? Original 0.5. The question asks you a position of Stretch point 2, meaning what is the length of scenario you want to investigate with this. 0.5 plus zero point 0.2, the final length that you have here is 0.7. Okay, and so on. So your velocity d2 is again tangent to the curve. So you have vd2 here. So vd1, vd2. Okay, so I just split into, I think this one, I draw it too fast. But so I can split this component. I can split this vd2 component into two. One in this direction, one is along the direction, or you can say as your normal and tangent direction. This is tangent, this is normal direction, or the R direction. Okay, this I already explained. The total length, the situation you want to investigate is when it's stretch point 2, so the total length here to here is 0.7. Free body diagram always have a weight pointing down. Contact surface always have an N. These two balance each other. And there's a force pointing in the center. Again, this tree doesn't work anything when it comes to principle of impulse and momentum. All right, because FC move along the radial, it doesn't do any moment. All right, these two balance each other, so in the equation you don't need to put inside there. Okay, I put this free body diagram on the right, and I start applying the conservation of angular momentum. So angular momentum before equal to angular momentum after. So what is angular momentum? Momentum multiplied by the distance. Momentum before. What is momentum? Mass velocity. It is here. Before. Multiplied by the R. What is this one? You have your R1. You have your M. You have your VD. So basically before you can calculate. After MOM. All right. What is momentum definition? Mass multiplied by velocity. Momentum multiplied by distance, you get MOM. What is the R2? R2 is here. You know your R2. You know your mass. You do not know your VD2. So only one unknown is here. This one you don't know. This one you have. 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 Substitute the value, you find this one. Okay. Important is application of conservation of angular momentum. Understand the definition of what is this, what is angular momentum. Balance before and after, you will find the unknown. So this is unknown. Put to one side. So VD2, which is the tangent direction. VD2, the tangent direction, 1.07 something meter per second. Next, what you do, you use conservation of energy. Why we use conservation of energy? Because we have spring force here. Because we have spring force here. Right? So anytime you see spring, you see an object moving from one location to another location, conservation of energy will be very useful in calculating velocity, height, distance, and so on. Yeah? So energy before equal to energy after. You cannot destroy energy, but energy can change form to another one. All right, it's conservation of energy definition. In this case, in this module, we only have two kinds of energy, kinetic and potential. Kinetic potential before equal to kinetic potential after. What is the equation of kinetic energy? Half mv squared. What is the potential energy? mgh. Okay. So here your potential is not height, but is the spring potential. Okay, it's a spring potential. So kinetic equal to mv squared. You are familiar with this. All right. Kinetic equal to half mv squared. Just substitute the value here. Half mv squared. Again, on the left hand side is before. So potential in this case, because you are using elastic object, you have the spring potential energy, half kx squared. Okay, if you forget, go back to the chapter 3. Right. Then this side also same, half mv squared plus half kx squared. You have this one. You have this one. You have the k given in the question. X, you know, right? And then this one, x here is the scratching, x is the displacement. If you don't pull the spring don't have potential. So during start, you don't have potential, although the formula is there. The x there means there's no stretching before it starts. So your x is 0. Here, your spring is stretch 0.2. Substitute 0.2 over here instead of 0.7. Don't use the wrong value. Potential energy is for the spring is how much you pull or compress. This is you stretch the elastic material. Substitute all the value. Before spring 0. The rest is substitute. Okay, you only have one unknown there, which is your VD2. Okay, use your calculator, calculate. You find VD2 equal to 1.36 meter per second. Whereas VD2 is the resultant of your VD2. Okay. So you have the resultant, you have the tangent direction, you have the radial direction, or you have normal direction. You have these two, right? You have these two. You are lack of this one. You can find from the Pythagoras theorem on how you find the resultant earlier. Same, but you flip the concept. Okay, earlier you have these two, you find resultant. Now you have this one, you have this one, you find the missing part of this one. Okay. Use the Pythagorean theorem. Your VD2 in this direction will be 0.8 meter per second. Okay. From here to here is here to here is engineering dynamics. Here onwards is mathematics. Right, linked with Pythagoras theorem. Okay, any question for example 11? Good, everyone?
Yes, so far okay, sir.
All right. Okay, let's go for a bit more. So for 4.8, I will go very fast, all right? Meaning I won't ask you in the final exam, right? Although this one is part of your module content. So what does this 4.8 steady flow of the float stream? This one you'll see when you study about float mechanics in coming years. I mean, after this, maybe you study about flow mechanics. You will look into principle of impulse or momentum. Again, you apply the principle of impulse momentum in the fluid stream, but when you take the fluid mechanics later, you will look into a more complex mathematics, right? But the concept still same. Huh? So you have water go in and water go out. I mean, you get the concept. Huh? Water go in must equal to water go out when you use principle. Huh? Something you go in must same as something you come out. Okay. Only what is different is the change of direction. The change of direction of your velocity vector. Right. Okay. Um, you will see this one again when you come to fluid mechanics later. What does this tree diagram tell you? It tells you that the transformation of liquid from before and after. Okay, before and after. This is time, change of time. This is after the time. So you see the liquid here. In this case, we focus on the control volume here. You see this one, the momentum go inside here, plus the change of impulse, the force acting on the surface inside, equal to the total momentum and impulse, like what you learned here. But this one is focused on the force acting on the vessel or on the wall. Huh? Okay. So this one is basically what you learned before this, but this one is more on the fluid, apply more on the fluid mechanics. Um, this one is before, the momentum before plus impulse before equal to momentum after. Okay, so the equation is focusing on this section, momentum or momenta. Momentum before is the mv. So you have two point of interest, A and B. So that's why in the equation, you will see momentum at A, momentum at B, plus the impulse. Impulse is integration of Ft and momentum after. Okay, and then you arrive at this equation. Principle of linear impulse. So all the momentum and impulse you put on the left-hand side equal to all the momentum after the incidence. Okay, so before you have momentum mv, but the center plus the center one, center also have momentum mv, point A and point B, and then the impulse ft plus the after. After you have flowing out, you have momentum because change of the size of the outlet, the velocity different, change of mass also different. So you have mv at this point plus the momentum at the center of the pipe. Okay, this is scalar. This is vector form. When you see cross means you work in a three-dimensional calculation. So this is principle of angular impulse and momentum. You see R cross something, R cross something, R cross something, and so on. Okay. Then you do some modification. You divide both with dt. You arrive at this one and this one. Huh? So this one arrive at this one arrive at this one. And usually we use incompressible fluid or continuity of mass. This one you learn in your fluid mechanics. More detail in fluid mechanics. Okay, the rest you can read from my slides. And example you can read, okay, example you can read. Again, for your info, for your batch, I won't ask this section, right? But again, you'll see this one in your fluid mechanics module, in your more senior years subject. Okay, with this, I conclude chapter 4. Tomorrow we do chapter 5. Okay, I end the recording.